Hello students. So in today's class we will try to understand the apparent forces. We have seen the origin of apparent forces. Why do these apparent forces come into picture, or what is the role of these apparent forces? So apparent forces are only the reaction terms of the inertial forces. That means, so if you want to account for the motion of the reference frame or non-inertial frame, if you want to account this particular non-inertial frame of reference, then you have to add few terms in the forces. So these forces are generally called as the apparent forces. Now, one very important thing is, if you consider a frame of reference which is let's say which is rotating or which is moving, any object which is considered to be at rest with respect to this frame is indeed is neither at rest nor in uniform motion. So the point is, you have a frame of reference which is moving with a velocity which is changing with magnitude or in direction, and this object, if it is also changing or if it is moving with a velocity, this object's velocity is to be described, or this object's motion is to be described with respect to the frame of reference and with respect to the frame of reference which is moving in nature. So here we use what are called as the apparent forces. Fine. Now, so in continuation with our discussion, we have already learned what is the centrifugal force, how does it come into picture, and how does it modify the gravity, how does it modify the direction of the gravity, and why the apparent gravity points away from the center of the earth, and how is it responsible for creating the bulge that you see on the planet Earth near the equator, right? So in today's class, what we will try to do is, we will try to extend the understanding of apparent forces so that we can formulate or we can derive expression for the Coriolis force. So today's class is going to be about Coriolis force and curvature effect. Curvature effect. Okay. So Coriolis force is a very important part in our discussions. Is going to play a very important role in many of the atmospheric motions. So because the Coriolis force effect is the one which tilts the direction of motion of an object which is traveling or which is moving with respect to a moving or rotating frame of reference. Okay. So for an object which is in motion relative to a rotating frame of reference, we need to consider two things. So for an object moving with respect to a rotating frame of reference, rotating frame of reference, we need to consider two very important things. One, change in the relative angular momentum of the object. So we have to consider change in the relative angular momentum of the object, relative angular momentum. Secondly, we need to add an additional centrifugal force, an additional component which is called as the centrifugal force. Fine. Now let us consider, let us consider an object of unit mass on the surface of the earth. Now let us say you have the earth. Let us consider an object which is moving on, which is at rest with respect to the earth. Now the earth is rotating from west to east. How fast does the earth rotate? If you want to calculate the angular velocity of the earth covers an angular displacement of 2 pi radians over 1 day, so which is 24 hours into, so this will be the angular velocity of the earth in radians per second. Okay, so what it means is that, so there is an angular velocity component with respect to earth. So earth travels at this speed, it covers this many radians per second. So if you consider an object which is at rest on the surface of the earth, just on the surface of the earth, let's say. So, this object can be considered to be moving at the angular velocity of the earth. Yeah, as long as it is at rest. If the object is moving by itself, if it has its own velocity, so then that velocity has to be added to this angular velocity of the earth. So, in this case what I have done is omega, capital omega is the angular velocity of the earth, and u by r is the angular velocity of the object. So, this is, so you add this when the object is moving with respect to the earth. Now, what we have a situation in which the object is moving with respect to the rotating frame of reference. Okay. So, object has its own velocity and a velocity component due to the earth itself. Okay. Now, the angular momentum in this case, angular momentum is equals to, can be written as m r square omega. So, here let us say r is the distance from the center and omega is the angular velocity. Okay. So, and the resulting torque can be written as r cross f. Okay. So, the angular momentum on the surface of the earth is given as m r square omega. If you take the radius of the earth to be capital R, then you write as m r square omega. Okay. Now, this angular momentum will remain a constant as long as there is no torque. So, if there is no torque that is acting on the body, the angular momentum will remain conserved. So, it will stay the same as long as. Okay. So, for let us say for an air parcel, let us consider an air parcel, the angular velocity, if the air parcel has, let us consider an air parcel consistent with our description of the air parcel with which has a velocity u. Okay. Now, if this air parcel is at a distance of let us say small r from the center, then the angular velocity of the air parcel would be omega plus omega. So, small omega is the angular velocity of the parcel with respect to the rotating frame of reference, and omega, capital omega is the angular velocity of the earth itself. So, which can be written as omega plus u by r, omega plus u by r, right. Now, let us say that the air parcel is moving. So, now it is moving, this velocity is called as zonal velocity. Now, let us say in order to be able to identify the different directions of motion or different components of velocity, what we do is we consider the earth, let us say. So, any movement in this direction, let us say from, so this movement is characterized from north to south, from the pole towards the equator or towards the pole, is called as the meridional motion. And any movement in this direction, let us say from west to east, is called as, from west to east is called as zonal motion. Okay. And any movement starting from the ground is called as the vertical motion. So, this, so when the object is displaced, is said to be displaced in meridional way, in meridional direction, then the object is changing, is changing latitudes. So, with time the object is travelling across the latitudes. When the object is said to be displaced in zonal direction, then the object with time is changing longitudes. Okay. When the object is displaced in the vertical direction, so considering generally what happens, let us say if it is at a very brief instance of time, if the object is displaced in the vertical direction, then the object is changing in altitude. Okay. So, latitudinal displacement leads to meridional motion, longitudinal displacement leads to zonal motion, and altitudinal displacement leads to vertical motion, as simple. Now, you also identify this direction. This is generally, let us say this is generally the u, the velocity component in the meridional motion is generally u. No, velocity component in the zonal motion is generally u. The velocity component in the meridional motion is generally taken as v, and the velocity component in the vertical motion is taken as w. Now, Now, this particular air parcel that we are talking about, so the situation is very simple here. The situation is such that we have an air parcel which is on this frame of reference, or let us say Earth. This is the air parcel. Now, the air parcel has its own velocity in the zonal direction, which is small u. This velocity gets added to the angular velocity of the Earth, which is omega. Okay. And if it is the case, so we have identified the directions of motion, we have named them, and we have also named the directions, the velocity components along these particular directions. Fine. Now, it is clear that now the air parcel is moving ahead zonally with respect to Earth. I mean, since it has its own velocity component, it is very easy to understand why it is moving ahead with respect to the Earth. So, it is moving ahead with respect to the Earth. So, before moving ahead, we need to understand the fundamental conservation, what needs to be conserved. So, one thing, as long as there is no external torque applied, the angular momentum will remain a constant. So, m r square omega will remain a constant. Okay. Now let us say now this object is having its own zonal velocity component. Now, the angular momentum of this parcel, now since it is having its own velocity component, the angular momentum of the parcel angular momentum of the parcel can be written as m r square omega plus u by r. Okay. Now, so this is the angular momentum of the parcel before it when it is moving with a zonal velocity component u. Right. So, zonal velocity is given as u. Now, let us say that the air parcel is slightly displaced such that its radius from the center changes from r to r plus delta r. So, you are going to displace this air parcel slightly in this direction, let us say in this direction, such that it changes from r to r plus delta r. Now, what is going to be the consequence? Simple. What is going to be the consequence is that now the object is moved by applying an external force, and so that its the value of r changes from r to r plus delta r, then the object will try to conserve the angular momentum. How does it conserve the angular momentum? The only other quantity in this angular momentum, let us say in this angular momentum that can be changed, of course, mass cannot be changed. You are trying to change r by this magnitude, by delta r. Omega, the capital omega, is the angular velocity of the Earth, which of course cannot be changed. The zonal velocity of the object is the only other physical quantity which can change so as to maintain the equilibrium in terms of angular momentum, or maintain the conservation for the angular momentum. So, as a result of r going to r plus delta r, the object will try to change its velocity from u to u plus delta u, such that angular momentum is conserved. Angular momentum is conserved. Okay. Now, what we can do is let us work out the conservation as such. Let us say what was the angular momentum before, and if the air parcel is displaced by a small magnitude, what will be the angular momentum afterwards. And in this picture, let us try to get an expression for delta u by solving the conservation of angular momentum. Okay. Now, let us due to the, so it is natural to expect. So, the new angular momentum would simply be r plus delta r whole square into omega plus u plus delta u by r plus delta r. What is this? This is the angular momentum after the external force is applied. External force is applied. Okay, fine. So what we can do is, let's say, so this is the angular momentum after the external force is applied. Now let us equate, let us try to conserve the angular momentum. Conserving the angular momentum, we can write r plus delta r whole square into omega plus u plus delta u by r plus delta r should be equal to r square times omega plus u by r. Now the basic idea is, if you apply an external force and change r, by solving this conservation, you should be able to find out what will be delta u, so as to equate this conservation always. Okay. So now this simply we will solve this. So we will write r square, mass gets cancelled anyway, r square times omega plus u by r is equals to r square plus delta r square plus 2r delta r times omega plus u by r plus delta r plus delta u by r plus delta r, which you can write as r square u plus r square u by r is equals to r square omega plus r square u by r plus delta r plus r square delta u by r plus delta r plus 2r delta r omega plus 2r delta r u by r plus delta r plus 2r delta r delta u divided by r plus delta r. Okay. Now in this, let's say in this equation, let's say this equation is A, or let's say this equation is A and this equation is B. Now neglecting all terms in the second order terms of delta, neglecting this second order del square terms, we can write r square u by r is equals to r square u by r plus delta r plus r square delta u divided by r plus delta r plus 2r delta r omega plus 2r delta r u divided by r plus delta r, which can be subsequently written as r square times u by r into r plus delta r is equals to r square u plus r square delta u plus 2r delta r omega into r plus delta r plus 2r delta r u. So which can be simplified by multiplying this into the bracket, which will be u r square plus u r delta r is equals to r square u plus r square delta u plus 2 r square delta r omega plus 2r delta r square omega plus 2r delta r u. So, this is the second order term in delta r, so that can be neglected and these two terms get cancelled. So, as a result what you have is we have r square delta u plus 2r square delta r omega plus 2r delta r u minus r u delta r is equals to 0, which can be written as r square delta u is equals to minus 2r square delta r omega minus r delta r u. So, delta u can be written as minus 2 omega delta r minus delta r times u divided by r. So, the velocity should change by this magnitude so as to conserve angular momentum. Now, let us look at the geometry of this conservation, let us say. So, this is the change in the velocity which the object has to do by itself so as to keep the angular momentum constant. Why should the angular momentum be constant? Because you have changed the value of capital R by some magnitude. So, the angular momentum should conserve in this picture. Right. Now, let us look at the geometry of this capital R with respect to the radius of the earth. So, we can simply say that you have, let us say, the radius is given as a, and if the object is here, the object's distance to the axis of rotation is capital R. Okay. So, if this is the center, so if this is the center, then the radius is small a. So, let us look at the geometry. So, now what we can do is we can consider the surface of the earth like this. Let us say okay. Now, this distance is small a. So, for reference, small a is the radius of earth. Okay. Now, so in this case, let us say this is r naught, r capital R itself, and this becomes r naught plus delta r. So, this angle is, by the way, can also be called as the latitude, and this angle becomes phi naught plus delta phi, and delta phi is a small angle. Okay. Now, you have caused the displacement in this direction, and so this distance can be called as delta y, and a is also given. So, by default this angle becomes phi naught. So, you have to understand this picture. So, this is the point where the air parcel was located, and you have changed this distance by applying an external force, and it has moved by a distance of delta r. Okay. Now, looking at this geometry, what we can do is we can go back to our expression of delta u and see how these quantities can be implemented into that. So, delta u is given as minus 2 omega delta r minus delta r times u divided by capital R. So, for reference, let us say delta r is the delta r arises due to external force, u is the air parcel's original direction of motion, zonal velocity, u is the zonal velocity, delta u arises due to the conservation of angular momentum. Right. Then we will see how this particular, so this is along this direction, it is the lat, and along this direction is the long. So if you displace it, now let's say, so let us see how we can implement this geometry into this particular equation and see how we can get the velocity components. So from the coordinate system, from this coordinate system, we can simply write r is equals to a cos phi, right, simply. So delta r can be written as a times minus sin phi delta phi plus cos phi to delta a, or delta r is equals to a times minus sin phi delta phi plus 0. So this delta r can be used in this expression. Okay, so let's see. So this is the basic idea of the how the conservation of angular momentum will lead to the development of change in the velocity along the zonal direction. So delta r is changed in a particular direction, and we are already expecting velocity change in the delta u direction. Okay, so the object has been displaced meridionally, and this displacement has led to the change in the velocity in the zonal direction, and this the main reason for this is the conservation of angular momentum. So we will continue this mathematics, and we will see how we can use this mathematical formalism to understand the Coriolis force. Okay, thank you.